Welcome to our journey of differentiation and integration, where we continue on our tale of slopes and expectations. Previously, we were crawling through the adjoint passage, and which is one of three ways of thinking about how to use differentiation. We will get now to the lake of Lagrange, where we can swim a little bit in the problems of constrained optimization. In this lecture, we will look at the method of Lagrange, which is a way of estimating gradients when we have constraints. In machine learning, we use gradients quite often to train predictors, and for functions where we can obtain this gradient directly, we know how to do this efficiently. However, we may wish to calculate a gradient for functions that have constraints, in particular inequality constraints. We assume, of course, that we can already calculate gradients for the corresponding unconstrained problem. Okay. The key idea that you will learn in this lecture is how to take the gradient with respect to a constrained optimization problem. The method of Lagrange was named after Joseph Louis Lagrange, who worked on calculus of variations in the 1700s. He founded this idea, and it was popularized in nonlinear programming by Karush Kuhn and Albert Tucker in 1951. It turns out actually that William Karush already discovered the conditions that you will see today, and they're now called the Karush Kuhn Tucker conditions. What was interesting about William Karush's discovery was that it was really just unknown for another 25 years before reintroduced back into the literature, which brings me to the point that you should read classic papers, and one paper that already looks at the relationship between backpropagation and Lagrange multipliers was the classic backpropagation paper by Jan LeCun in 1988. So what is a constrained optimization problem? Let me set it up here. We have a function f, which we call the objective function. The function takes a vector x of d dimensions and gives us a scalar value. We want to minimize this objective function, but we have constraints on what values x can take, and these constraints, these m constraints, are expressed by functions gi. That's written there. This is called the primal optimization problem, in contrast to something that we'll see a little bit later called the dual optimization problem. One way to convert from a constrained problem to an unconstrained problem is by introducing a simple function like the step function here we see here. If the constraints are satisfied, then the function returns 0. If the constraints are not satisfied, then the function returns infinity. Okay, and we can just now combine the objective function f with the constraints gi in one single optimization problem, like written on the top of the slide as j here. Okay, now this problem is now unconstrained, but it has this really difficult infinite step function. Okay, this function, this indicator function, makes it very hard to optimize because it's hard to compute gradients, and you end up with this combinatorial optimization problem. Okay, the key idea for Lagrange multipliers is to do a relaxation of this type of function. So instead of an indicator function, we introduce a Lagrange multiplier. Okay, so same as before, we write down the objective function f, and we add the constraints to the objective function. Okay? Now, instead of adding it in terms of an indicator function, we add it with a weight lambda. Okay? These weights lambda are called Lagrange multipliers, and the overall term altogether is called the Lagrangian, as shown on the slide here. So why do we consider the Lagrangian? The Lagrangian is nice because firstly, it's an unconstrained problem, as you can see. Now it's unconstrained for a given value of lambda. So it remains to be seen how we choose the value of lambda. It turns out that if solving the Lagrangian is easy, so finding the minimum of the Lagrangian is easy, then the overall problem is easy. The key thing that happens is that we convert the primal problem in terms of the variable x of d dimensions to a different problem now in terms of lambda. And remember that there's a lambda for each constraint, so there are m values of lambda. It turns out that this primal problem that we saw before and the dual problem, the problem that you will see in the next slide, they're actually related. They're related in this very strong way by the gradients at optimality. Okay, so we will see that on the next slide. It turns out that the dual optimization problem is actually a very nice problem to solve, even though the function f, the objective function f, and the constraints g, they might be non-convex, but the dual optimization problem is still convex. Okay, so you've seen the primal optimization before, where we minimize the function f subject to constraints gi. The Lagrangian dual is given by the maximization over lambda for this function d, where d is essentially the Lagrangian. Okay. Now, one thing that we need to do to make sure that the problem is well posed is to constrain that the Lagrange multipliers are positive. Okay. So that's the dual optimization problem. Why is this duality useful? It's because the primal value, the value of the objective function f, is always greater than the dual value, the value of the optimization problem in D. Okay, and to show this we can use a basic fact called the Minimax inequality. The key idea is that for any function with two arguments, the maximin is less than the minimax. So in other words, as shown by the equation here, for any function phi of two arguments x and y, the maximum over y over the minimum over x is always less than the minimum over x of the maximum over y. This idea can be used to show that the primal values are always greater than the dual values. Okay. By just plugging in the definitions of the Lagrangian and looking carefully at how the minimum over x and the maximum over lambdas can be swapped, we can see that on the left-hand side of the equation here, in the term under the brackets, that is the objective function f, and on the right-hand side, we can see that the term under the bracket is the objective function d. Okay? And by observing that the left-hand side is greater than the right-hand side by the Minimax inequality, we can show that the primal values is always greater than the dual values. This relationship is called weak duality, and it always holds, and it allows us to build efficient optimization problems. So on to the Karush Kuhn Tucker conditions, which we mentioned earlier. Recall the Lagrangian. Okay, so as written here, which is the objective function f plus lambda times the constraints. The Karush Kuhn Tucker conditions consist of 4 conditions, and before we present them, I'd like to motivate them here. The first condition is called stationarity, which is the standard condition that we solve for the minimum of the optimal value by taking the gradient of the Lagrangian with respect to lambda and setting it to 0. You get the stationarity condition. The second Karush Kuhn Tucker condition is a little bit more subtle, and it's called complementary slackness. This is the condition that the Lagrange multipliers must be orthogonal to the constraints. Okay. The reason they are called complementary is because we have 2 variables, a primal variable x and the dual variable lambdas, and those 2 are complementary to each other. The constraints, the corresponding constraints on lambda and the constraints on g are complementary. Now, the word slack here means that if the variable has slack, it can further be optimized. Okay. Now recall that we have a lambda I, for each constraint gi. If you look at the Lagrangian at the top here, if lambda I is 0, then gi can take any value and not affect the value of the Lagrangian. Okay, this means that GI has slack. So if GI is 0, that means GI is active, right? Remember that GI is a condition which must be less than or equal to 0. If GI is at 0, that means GI is, that constraint itself is active. Then lambda I has slack, which means it can take any value. So at an optimum value, you're likely to be at the corner of the constraint set, and therefore one or the other of the optimization constraints have to be active. And so only one of them can be non-zero. Okay. Of course, we want to retain the feasibility, and that's what we add to the conditions. So just writing out the conditions here, the stationarity conditions are given by taking the gradient of the Lagrangian with respect to x. Complementary slackness says that either lambda I is 0 or GI is 0. Okay. And we have primal feasibility and dual feasibility. One thing interesting by staring at the constrained optimization problem is that you can look at the stationarity conditions, the first equation here, and notice that if the problem is stationary, if the value of x results in 0, then you can express the gradient of the objective in terms of a sum of the gradients of active constraints GI. Right? Just by rearranging for some given value of lambda, we have the gradient of the objective is the conic combination of active constraint gradients. The word conic here means that the value of lambda is positive or non-negative. Now, what's interesting about these conditions is together, the Karush Kuhn Tucker conditions are sufficient for zero duality gap. Okay? And we can see this by this quick proof sketch. By weak duality, recall that weak duality says that the primal objective function f is always greater than the dual objective function d. Okay, so we always have that condition that f is greater than d. We denote here by x star and lambda star the optimal values. From the stationarity conditions, we can see that the value of the dual optimization problem d at lambda star can be written out by the Lagrangian at lambda star and x star. And by observing that the right term is essentially a sum over the terms which are in the complementary slackness condition, we can see that the right term is 0 because it's either lambda I is 0 or GI is 0, right? And since the product is always 0, then that sum disappears. So we get the fact that the primal optimization problem is the same value as the dual optimization problem. Hence, the duality gap is 0. So what does duality gap 0 mean? It means that the optimization problem has found the optimal value, and this is a very strong constraint. It's worth repeating that the Karush Kuhn Tucker conditions are actually just sufficient for the zero duality gap. To get necessary conditions, we need an extra thing. And this extra thing is called constraint qualification, which we will not discuss further. The challenge comes from the fact that the geometric constraints that we have on the problem in terms of these equations have to be expressed in terms of algebraic equations, and that is challenging. In summary, we have seen how to take a gradient with respect to constraint optimization problem, and we have done this using the method of Lagrange. We have seen that if we satisfy stationarity conditions, which is taking the gradient with respect to the Lagrangian and setting it to 0, we get that the objective gradient is actually a conic combination of the active constraint gradients, as shown by the equation here. If we additionally check that one of the Lagrange multipliers or one of the primal constraints is 0, we satisfy the Karush Kuhn Tucker conditions. And if we satisfy the Karush Kuhn Tucker conditions, this is sufficient for achieving zero duality gap, which means that we have a global optimum. That's all for now. Thank you for your attention.